Today we're going to do our usual thing where I open up with a problem from Calc 1 and you think, what's this problem from Calc 1 doing here in Calc 3? And then after we go through this problem to remind ourselves how it works, we do a problem from Calc 3 that looks just like the problem from Calc 1. And we do the same thing. Although it's going to be a little bit different here because we've got 4 second derivatives instead of just the 1. Let's find out what we need to do. First, take a moment and find the critical points of this function, and then classify each one as a local maximum, a local minimum, or neither a local maximum or a local minimum. Go ahead and pause the video now and give it a try. I don't have any ads to run during the pause, but thank you, Fresh Tall Walker, for that format. Just like record and just let the video run while people work on the problem, and then come back and do the solution. If you don't know who I'm talking about, on YouTube, go to Mind Your Decisions. Lots of really cool videos there. Let's talk about what we need to do to find the critical points. The first thing is we want to find the critical points of f . And there are 2 things that make critical points. We usually forget the second one. We want to find the critical points by solving f prime equals 0. So these are either the zeros of the first derivative or places where the first derivative is undefined. So we're looking for f prime equals 0 or f prime is undefined. I do want to point that one out, that undefined part, because we usually forget, because a lot of times we're working with polynomials and we don't have to worry about it. Also, it's too early to do something fancy where the critical points are undefined. I can't like stand up here at the board and think of one of those problems. I would have had to have planned ahead, and we all know that I'm not really a planning ahead type of person. Once we have the critical points, we want to classify each one. And here we have some options in the classification department. One option is to check points near the critical points. Check for the direction of the function. Use the first derivative to check the direction of the function. So one strategy is to just continue on with the first derivative and use the first derivative to check the direction of the function in between the critical points. If we go from increasing to decreasing, then we've hit a local maximum. If we go from decreasing to increasing, we've hit a local minimum at that critical point. So increasing to decreasing is a local maximum. Decreasing to increasing will give us a local minimum. If the function doesn't change direction, so the function increases, flattens out, and then just continues to increase, then it's neither. Sometimes we'll call it a saddle point. That's using more Calc 3 style language. So that's how we can classify the critical points. Our other option for classifying critical points is to use the second derivative to check concavity. So option 2 is use the second derivative to check the concavity at the critical points. Check the concavity of the function at the critical points. If we find that the function is concave down because the second derivative is negative at that point, then we can imagine a local maximum. So if we get concave down, we have a max. If we get concave up, we have a min. So there are a couple of strategies to decide if we have a local maximum or a local minimum. Any questions? So let's go through this problem. Our function is x cubed plus 3x squared minus 9x plus 5. So our derivative, f prime of x, is 3x squared plus 6x minus 9. And to find the critical points, we want to set this equal to 0. Unsurprisingly, this ended up with a factorable polynomial, which is a little bit cheap on my part, because I spent like a couple days ago, like just trashing the quadratic formula, and yet I went with a factorable polynomial here. So lame. Why don't you pick something that use your fancy completing the square? I also cheated in that department too, because look at the middle term. It's got an even coefficient. So if I wanted to complete the square, I would have made it easy on myself. So if anybody's like, oh, if you don't hate the quadratic formula so much and factoring is so stupid, why don't you complete the square in this one? Then I could be like, oh, well, fine, I'll do that. But I cheated again because b is even. Incidentally, completing the square is you look at the x squared plus 2x and you figure out what constant will make this a square trinomial. Half of 2 is 1. There's the cheating part. Squared is 1. So this polynomial is x squared plus 2x. And if I put a plus 1, that will give me an x plus 1 squared. But then I have to figure out, since I've got a plus 1 there, overall, I still need to have a minus 3. So I need to have the next term be a minus 4. Plus 1 minus 4 is a minus 3. The other thing that you could do is write a plus 1 for the plus 1 and then a minus 1 after the minus 3 to figure out that you need a minus 4. Or you can just know that that's what the process is. It's figure out how much to separate off from the plus 3. I need to subtract 1 from the minus 3 to get the plus 1 for the complete square. That leaves me with a minus 4. So the reason that this is useful is that we get our square trinomial. And now we can see what the solutions are. -1 plus or minus 2. Because -1 is the x coordinate of the vertex. And then the minus 4, we're down 4, so we just plus or minus that value. It came out minus, so we know we have 2 solutions. And notice -1 plus or minus 2 is going to be 1 and -3. So we still get the same critical points. I'm going to write it in this form. So if you start computing the square, you can look at that -4. The odds, the h plus or minus the square root of that constant. Or the square root of the opposite constant. So I did make it easy on us by making this polynomial factorable, because factoring the polynomial wasn't the point, but apparently I can't walk by a factored polynomial and not trash the quadratic formula. Oh well. So we have the locations of the critical points. We have critical points at 1 and -3. We've got to figure out whether we have a local maximum or a local minimum. Now, if we look at the polynomial, we could skip this derivative business and just think about what the polynomial looks like. It's cubic with a positive leading coefficient. So we can skip this whole derivative business and know that this must be what the function looks like. It's cubic with a positive leading coefficient. So the limit as x goes to infinity must be positive infinity, which means the other end is negative infinity. There are two critical points, so it most likely turns around twice. It looks like -3 is going to be a local minimum and 1 is going to be a local maximum. The thing that we do have to worry about is if one of these points just goes flat, but that's not going to happen because look at our derivative. So I want to use the second derivative to check. So f double prime, it's going to be 6x plus 6. And then we'll just plug in our two critical points. Oh, it's color coded now. I can't stop. -18 plus 6 is -12. So this tells us that the function is concave down when x equals -3. And that makes us believe that -3, f has a local maximum, sorry, yes, maximum at -3. I wrote them in this order. I thought them in this order. So I calculated them in this order, but I was still thinking in this order. So this tells us that f is concave down and then we can conclude that f has a local maximum at x equals -3. Then we need to check the one and the other thing is going to happen. So f double prime at 1 will be 6 times 1 plus 6. So it's going to be 6 and 6, 12, which is positive, which tells us that f is concave up at 1. And so we'll conclude, of course, is the outline of our strategy. First derivative to find the critical points, second derivative to classify the critical points. We can also break up the x-axis into before -3, between -3 and 1, and then after 1, and decide whether the first derivative is positive or negative in each of those intervals. As we know, the two places where first derivative is 0, and that will tell us that the function changes from increasing to decreasing or from decreasing to increasing. With all this information, we know that this is what the function looks like. So we find negative before -3, positive before -3. First derivative will be negative between -3 and 1, and positive after 1. Any questions? Yes. Yeah, if the function just flattens out and then keeps going, then the second derivative will show up as 0. And remember, second derivative equals 0 means an inflection point. We're changing concavity. So we would see, if we see second derivative equal to 0, we would see concave down before and then concave up afterwards. So it would warrant some additional investigation. So you can grab your first derivative and look at what's going on either side and see that it's increasing on both sides. It doesn't necessarily mean there's an inflection point just because the second derivative is 0. That's, I think, an important thing to remember. Because if you think of the function x to the 4th, the first derivative is 4x cubed, and the second derivative is something x squared. And so the second derivative will be 0 at 0, but it's still a local minimum because the function isn't changing concavity. It's concave up, and then it's concave up. So we've got to, if there's the second derivative equals 0 does not necessarily mean an inflection point. It's a possible inflection point. It only seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. Question? I think you so that's depending on the concavity. So once we find the critical points, here are the points where the first derivative is equal to 0. And that means that the function has flattened out. And we're just trying to decide if the function flattens out and changes direction, flattens out and changes direction, or if the function flattens out and then keeps going in the same direction. So by looking at the second derivative, so here's our two critical points. This is where the function is flat. When we look at the second derivative at each of those points, we found that at -3, the function was concave down. So that tells us that the graph must look like concave down, and that indicates a local maximum. And then at 1, we found the function was concave up. But those 2 points are where the first derivative is equal to 0, which means that the function is flat. We interpret first derivative equals 0 as function is flat, neither increasing nor decreasing. Now the next part is super predictable. There are no surprises here. I'm not going to say f of x equals. I'm going to say f of x y equals. Ooh. But I'm definitely stealing a function, so it'll work out the way I want it to. I also wanted something with a combination of x and y, like in one term. Otherwise, my typical thing is just be like all 4 minus x squared minus y squared. And everybody looks at it and they're like, oh, that's just a circular paraboloid. It's got a maximum of 0, 0, 4. Because I can picture it. So I go with this. It's like, well, what does this one look like? And you're like, well, I don't know. Like, oh, good. Now we have to use the equations to find out. This is an important skill. A lot of times we're told, draw a picture so we can get a good idea. But the reason that we draw all those pictures to get a good idea is not because the strategy is always going to be draw a picture so we can get an idea of what we're dealing with. Because once we start dealing with shapes in higher dimensions, we don't have pictures that we get to rely on anymore. Fourth dimension, I mean, we could just look at slices. The slices would just be solids and we could go that way. But fifth dimension, if we want to picture it, we're going to have to cut out 2, find a way to cut out 2 dimensions so we could look at slices in 3 dimensions. Ugh. Then it gets messy. We've got to start thinking in terms of the Matrix. Everybody remember the movie The Matrix? I realized that movie came out before everybody here was born, but have you seen the movie The Matrix? That old movie, The Matrix. It's an old movie now. I think people need to realize that. people my age like, oh yeah, the Matrix. And like kids these days, they're like, oh yeah, that old movie. And I go, what? That's not an old movie. But it came out, it's like The Godfather is an old movie. When I was in my 20s, The Godfather came out when I was born. So in 1991, The Godfather came out like in 1970 or 71, something like that. Anyway, I was too young to see it when it came out with that one because I was a baby. And you don't take babies to The Godfather. Mostly because it's loud. It's not like I would have remembered anything. But then, when I'm starting off as an adult, when I'm a proto-adult, I go, oh yeah, that old movie. And people around that saw it in the theaters when it first came out, they're like, oh, that's not an old movie. Is that an old movie? Welcome to the Matrix. But anyway, in the Matrix, they're like looking at the screen, and it's not a visual representation of what's going on. They don't render any of the images. It's just a bunch of green symbols floating down the screen, right? That's what monitors used to look like. They were just like monochrome, and it was like that weird green color. And it was just like symbols floating around the screen. And they had to train themselves to see the images in the symbols. You have to train yourself to see the image in the symbols. This has to spark off this kind of look. You see this in these symbols. When we look at the parabola on a simpler level, when you look at this 3x squared, you're imagining a parabola. That 3 means that parabola is going to be pretty skinny. It's a positive 3, so you know it's going to open upwards. But you see the picture from the symbols. That's what they were doing in the Matrix. You know what I mean? I had this discussion with my friends. I don't think they figured it out. I tried teaching them math, which is why I think they were just rejecting everything that I said. They're like, well, how can they see any pictures in that? I'm like, oh, what does x squared look like? They're like, it's a parabola. Well, which way does it open? And it's like, it opens up. What if I make it a 3x squared? Then it's skinnier. And then I'm like, oh, so if you see it, and they're like, oh, stop teaching us math, Leach. Zip it. I'm like, well, then I want you to stipulate. I want defense to stipulate that they can see the pictures in the green symbols floating down the page. And they said, okay, just to shut me up. So that was effective enough. You know what I mean? So we don't know what this one looks like. But here's our task. Find the critical points. Critical points mean the first derivative is 0 or undefined. Polynomial, so we're not worried about the undefined thing. But I don't just write f prime equals 0, because I don't just have an f prime. What do we have instead? Here, we have 2 derivatives. There's an fx derivative and an fy derivative. And we're going to want them both to be 0. We're going to want to see this surface. Remember, this is a surface, not a curve. We're going to want to see it flatten out in the x direction. And we're also going to want to see it flatten out in the y direction. So we want to see it flatten out in the x direction and flatten out in the y direction. It's going to have to be both so we can get that one point that's sticking out above all the other ones. That high point is going to be flat in the x direction and flat in the y direction. I'm going to want to put a flat tangent plane at that point if we've got a local maximum or a local minimum. That makes sense? It's important that I say f of x equals 0 and, sorry, not f of x, fx equals 0 and fy equals 0, not or. And if you start writing shit with and/or, just write or. That's what it means. I hate and or. Or means and or. This is a hill that I'm going to die on. No, but or means and or. Anyway, so I want both of these derivatives to be 0. Let's do that. Let's not worry about the classifying part. Let's just find our derivatives. So fx see, this is constant. 8y cubed is constant. Derivative of 12x squared is going to be 24x minus 24y. So the 8y cubed is a constant term with respect to x. And in the last term, negative 24y is a constant factor with respect to x. For fy, the derivative of 8y cubed is 24y squared. The 12x squared is a constant term with respect to y, so the derivative is 0. And over in this term, the negative 24x is a constant factor with respect to y. It's being multiplied by y. So the derivative of negative 24xy, negative 24x. Any questions? We haven't had extensive practice on finding first partial derivatives, but here we are. Already getting pretty good at it. So what we've ended up with, we're going to set each of these equal to 0 because that's our strategy. Take the first derivatives and set them equal to 0. And instead of ending up with an equation that we need to solve for x, we end up with a system of equations that we have to solve for x, y. So instead of just an equation in x, we end up with a system of equations that we need to solve because there's an x and a y. Moreover, the extra exciting part, it's a nonlinear system. Not a very interesting nonlinear system, but it's a nonlinear system, and that's pretty cool. We can divide 24 out of both of the equations. Any questions? Yeah. So in the 20, when we look at 24xy with respect to x, 24 and the y, those are constants. They're constant factors. So just focusing on this term here. So with negative 24xy, negative 24, that's a constant with respect to any variable. But for fx, y is a constant factor. It's being multiplied by the x. And in fx, we think of y as being constant. So for fx, think of y as constant. So that's the starting place. When we're taking the derivative with respect to x, x is the only variable that we see. Y is a constant. Correct. Because when we look at the 8y cubed and think y is constant, and it's included as a term. It's all just one term. There's no x in that term. There's no variable in that term. So the derivative is 0. So no x in this term. In both cases, I'm looking at the term and I'm saying for fx, y is a constant. In this first term, I think there's no x in here. This is a constant term. So constant term in this case. But in this term, there is an x in that term, the 24xy. So y is a constant, but it's included through multiplication, so it's a constant factor. Here's the other reason I wanted that xy mixed in, so that we can have practice with our first partial derivatives. It's like I planned this. Right now, everybody's saying, oh, that was a planted question. You might talk to Tony before class and say, hey, I need you to ask this question. Like a fake news magician, right? So perfect timing on the question. And that was the reason that we chose this one. So we have that term factor. And then the same thing happens for fy. For fy, x is constant. So this 12x squared, there's no y in that term. This is a constant term with respect to y. But over here, that negative 24x, that's a constant factor. Always think this is a x, the other variable is a constant. Is it a constant term or a constant factor? Oof, but now we got this nonlinear equation to solve, system of equations to solve. So we have to set our Wayback Machine to algebra and remember this section on solving nonlinear equations. If you're coming up empty in that search, that's because in algebra, you don't solve nonlinear equations generally. Only if your teacher is very fancy. You solve a bunch of linear equations, you learn like multiple techniques for that. But when you get to nonlinear systems, it usually shows up here in Calc 3. And you're like, oh, well, what's the formal system to use? And the answer is do something. Wait, what? Just do stuff. Just make it happen. So let's make it happen. We just got to make some stuff up. Substitution, elimination, just make stuff up. Because these equations came out so simple, I'm just going to draw a picture of what's going on. I got y squared minus x equals 0. That just says x equals y squared. That's a parabola, but it opens sideways, right? So I'm just going to draw a picture. Here's the origin. 1, 1, 1, 1, 2, 3, 1, 1, 1, 2, 3. So there's an image of one of our equations. At this point in your mathematical careers, you should be pretty well versed in drawing nice parabolas. So you start off with your vertex and 1, 1, 1, 1, and then from that point, over one more, and then 3. So it's a change in 1, changes 3, the next change would be 5. Or you can go 1 squared is 1, and 2 squared is 4. So however you want to do that. The reason that I wasn't worried about jamming this up at the top is that my other one is just y equals x. And so that's going to go through 0, 0, and 1, 1. I'm going to need the highlight color for that. Not blue, orange. I should have gone red, blue, and maybe intersections in purple. That would have been nice. I'm gonna have to do this whole thing over tomorrow. There are critical points. Those are the points where x is equal to y and x is equal to y squared. We could have solved that just by thinking about it, but I wanted to draw a picture. The next stage would be classify. I technically didn't ask you to classify these critical points because I didn't think I was going to get that far. And I didn't, just like I planned. But here's the thing that I want you to think about. What we did in the previous problem was use the second derivative to classify each point as a local minimum, a local maximum, or neither. The problem here is that we have multiple second derivatives because each function that I write has two derivatives, fx and fy. So the problem now is we have 4 second derivatives. Four second partial derivatives. fxx, fxy. That would be the derivative with respect to x, then with respect to x. fxy would be the derivative with respect to x, then with respect to y. And then fyy, I'm going to put fyx first, and then fyy. So fyx would be the derivative of f with respect to y, then with respect to x, and then fyy would be the derivative with respect to y, then with respect to y again. Also known as the student's second derivative, as it's fyy. So notice that I made a distinction between fxy and fyx. This is because you don't know right now that if everything's nice and continuous and well ordered, then those are going to be the same. But for now, there's just going to be 4. One will count twice. All right, that's going to do it for today. I will see you all on tomorrow, and we'll talk about this second derivative problem. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.